History is filled with silent structures that hold impossible secrets. We are about to explore 25 ancient structural innovations that reveal a shocking level of unexpected technical mastery. By the end, you will see the entire timeline of human achievement in a completely new light. How did builders create earthquake-proof walls without computers? What forgotten knowledge powered a device called the world's first computer over 2,000 years ago? This journey uncovers the hidden genius of our ancestors, proving their solutions were often as sophisticated as our own. What do you believe is humanity's greatest forgotten innovation? This mastery is not measured by age alone, but by the startling gap between what we assume ancient people knew and the evidence they left behind in stone and metal. True technical mastery in the ancient world reveals itself through three profound puzzles. First, material science. How did cultures manipulate substances like concrete or steel in ways we could not replicate for centuries? Second, logistical planning. Moving 100-ton blocks across miles of rugged terrain was not just about brute force. It was a complex feat of engineering and social organization. And third, astronomical alignment. Structures locked precisely to the solstices or star patterns imply a deep, sustained observation of the heavens, encoded into architecture. These three threads weave through every example we will uncover. They point to a sophisticated understanding of physics, mathematics, and the environment that often seems to appear fully formed, without the long trail of prototypes and failures we would expect. This absence of a clear evolutionary path is the core of the mystery. It invites us to question the linear story of human progress and consider the possibility of peaks of knowledge that were reached, lost, and are only now being glimpsed again through the silent testimony of these ancient innovations. High in the Peruvian Andes, a fortress wall defies every expectation of ancient construction. This is Sacsayhuamán, and its signature innovation is a stoneworking technique called polygonal masonry. Rather than using uniform, rectangular blocks, the builders selected enormous pieces of limestone, some heavier than 100 tons, and carved them into a dizzying array of complex, irregular shapes. Each stone is a unique puzzle piece, with multiple sides and angles that fit precisely against its neighbors. The result is a colossal stone tapestry, interlocking so seamlessly that for centuries, observers have remarked that not even a sheet of paper can be inserted into the joints. This was not an artistic choice, but a stroke of engineering genius. The irregular, interlocking fit created a structure with a flexibility that uniform blocks could never achieve. During an earthquake, the entire wall could shift and settle as a single, resilient unit, the stones grinding against each other without collapsing. This inherent seismic stability is why these walls still stand tall after enduring hundreds of years of powerful Andean tremors. Yet the mastery only deepens the mystery. How were these multi-ton stones quarried from a site miles away, transported up the steep mountainside? How were they shaped with such impossible precision using only stone and bronze tools? The method remains one of history's great logistical puzzles, pointing to a society that commanded not just incredible labor, but an almost intuitive understanding of material behavior and structural physics. This was not mere stacking, it was a dialogue with the landscape itself, creating a fortress that was literally woven into the bones of the earth. From the solid, earthquake-defying walls of the Andes, we traveled to the silent depths of the Aegean Sea, where a discovery lay hidden for 2,000 years that would rewrite our understanding of ancient technology. In the early 1900s, sponge divers off the coast of a small Greek island called Antikythera stumbled upon the wreck of a Roman cargo ship. Among the statues and ceramics, they recovered a corroded lump of bronze and wood, about the size of a large book. Initially overlooked, this unassuming object would later be recognized as perhaps the most astonishing mechanical artifact ever found from the ancient world, the Antikythera Mechanism. X-ray and modern scanning technologies have since revealed its true nature, a complex clockwork device consisting of at least 30 precise bronze gears, housed in a wooden case with dials and inscriptions on the front and back. It was, in essence, an intricate analog computer designed not for calculation in our digital sense, but for modeling the movements of the heavens. Built around 100 years before the Common Era, this mechanism could predict the positions of the sun and moon, track the phases of the moon, forecast eclipses years in advance, and even model the irregular orbit of certain planets. It was a portable cosmos, a simulation of the universe as understood by the Greeks, all powered by the simple turn of a hand crank. The true mark of its unexpected mastery lies in the engineering of its gear trains. One gear, in particular, has a central pin that slides within a slot on another gear, a design now recognized as a differential gear. This ingenious arrangement allowed the mechanism to account for the moon's variable speed in its orbit, a subtlety in celestial mechanics that requires sophisticated mathematical understanding to model mechanically. Historians of technology were stunned because this precise form of gearing was not thought to have been invented until the 16th century, for use in sophisticated clocks and later in automobiles. Its presence here, in a device from classical antiquity, represents a leap of over 1,500 years. This was not a prototype or a crude experiment. It was a finished, refined instrument, implying a lost tradition of high-precision mechanical craftsmanship and a deep, applied knowledge of astronomy. The Antikythera Mechanism shatters the persistent myth that ancient science was purely theoretical or observational. It proves that the Greeks, or perhaps an unknown school of artisans they inspired, had mastered the art of translating complex astronomical cycles into the physical language of interlocking bronze teeth and rotating dials. It stands as a silent, profound question: how many other such devices were made, used, and ultimately lost, leaving no trace in the historical record except for this one miraculous survivor from the seafloor? While the Antikythera Mechanism reveals a lost world of precision mechanics, another empire was mastering a different kind of material magic, one that would shape the very skyline of history. In the heart of Rome stands a temple that has defied time, weather, and even gravity itself for nearly 2,000 years. The Pantheon, completed around 126 AD, is crowned by a dome so vast and perfect it seems to float above the circular space below. With a diameter of over 142 feet, it remains the world's largest unreinforced concrete dome, a record unchallenged for over a millennium. Its survival is not luck, it is the direct result of a revolutionary innovation in material science, Roman concrete. The Roman formula was a masterpiece of ancient chemistry. While modern Portland cement relies on a chemical process that can weaken over centuries, especially in contact with seawater, the Romans created something more resilient. Their key ingredient was a fine volcanic ash called pozzolana, named for the town of Pozzuoli near Mount Vesuvius. When mixed with lime and water, this ash triggered a slow, long-term chemical reaction, creating a binder that actually gained strength over time and could even cure and harden underwater. This was not just durable concrete, it was a self-healing, eternally strengthening material. But the Roman builders did not stop there. Their technical mastery extended to brilliant structural design. As they constructed the Pantheon's dome, they cleverly varied the composition of the concrete itself. At the heavy, supporting base, the mix included dense travertine stone. But as the dome curved upward, the builders lightened the load by changing the aggregate, blending in lighter materials like porous pumice at the very top. This gradual reduction in weight was a critical innovation, preventing the immense structure from collapsing under its own mass. The result was an architectural triumph, a vast, open interior space flooded with light from the central oculus, a hole in the dome open to the heavens. For over 1,300 years, no builder in Europe could match this feat of engineering. The secret of the concrete recipe was lost with the empire itself, becoming one of history's great technological regressions. Today, modern scientists are actively studying samples of Roman concrete, using advanced tools to decode its molecular structure. Their goal is not just historical curiosity, but to learn from this ancient wisdom. They seek to understand its self-healing properties and incredible longevity to inspire new, more sustainable building materials for our own time. The Pantheon's dome, therefore, is more than a beautiful relic, it is an active classroom. It stands as permanent proof that some ancient solutions were not merely adequate for their era, but were brilliantly conceived triumphs of engineering that we are still striving to fully comprehend and perhaps even replicate today. The silent genius of Roman concrete shaped monuments for the gods, but another civilization solved a far more urgent challenge, one that meant the difference between life and desolation in some of the harshest environments on Earth. In the vast, sun-scorched plains and mountains of ancient Persia, water was not a luxury, it was the very currency of survival. Here, engineers performed a kind of alchemy, not turning lead into gold, but turning barren desert into flourishing garden. Their innovation was not a towering temple, but a hidden, whispering vein beneath the sand, the Qanat. This was not a simple well or an open canal. A Qanat is a masterpiece of subterranean hydrology, a gently sloping tunnel carved deep into the earth, often for dozens of miles. It begins at the foot of a mountain where builders would first locate a water-bearing aquifer. Then, with astonishing precision, they would dig a mother well to tap this source. From there, the true work began, tunneling a channel that sloped ever so slightly downhill, just enough for gravity to pull the water along its entire journey, but not so steeply that it would erode the tunnel walls. The gradient was everything, a calculation made without modern levels, requiring a profound, intuitive grasp of the landscape. But the Qanat's brilliance extended beyond its initial construction. At regular intervals, sometimes every 60 or 100 feet, the builders dug vertical shafts straight down from the surface to meet the underground channel. These shafts served a dual purpose. First, they provided crucial air vents and allowed the excavated soil and rock to be hauled out during construction. Second, and most ingeniously, they became permanent maintenance access points for generations of caretakers who would descend to clear silt and keep the life-giving water flowing. This design made the system self-sustaining. By running entirely underground, the Qanat solved two catastrophic problems of desert water management at once. It completely prevented the devastating evaporation that would claim a surface canal, and it protected the precious water from contamination and dust storms. The result was nothing short of miraculous. A Qanat could transform a dry valley into a sudden, sustainable oasis. Villages, and eventually great cities like Persepolis, would spring up at the terminal point where the cool, clean water finally emerged into a sunlit basin or irrigation network. This was not a technology of conquest, but one of profound harmony. It required a deep, collaborative understanding of geology, hydrology, and community planning. Some Qanat systems are so ancient their origins are lost to time, yet many remained in continuous use for over 2,000 years, a testament to their flawless design. In a world now facing its own water challenges, the Qanat stands as a quiet, powerful lesson. It demonstrates that the most advanced technical mastery is not always about imposing our will on nature, but about listening to the land, understanding its hidden rhythms, and crafting a solution that works with the immutable laws of physics to nurture life for centuries to come. The Qanat's hidden channels mastered the flow of water, but another civilization sought to channel something far more abstract, the very movement of the cosmos itself onto the earth. This ambition finds its ultimate expression in the stark desert plateau of Giza. While the overwhelming scale of the Great Pyramid is what first strikes any observer, its true, unsettling genius lies in a precision that borders on the impossible. Consider the foundation. The pyramid's base, covering over 13 acres, is leveled to within less than an inch across its entire expanse. On a construction site today, with laser levels and digital theodolites, this would be an impressive feat. Achieved over 4,500 years ago with the tools we assume were available, it defies easy explanation, but the precision only deepens. The four sides of the pyramid are aligned to the cardinal directions north, south, east, and west, with an error of just a fraction of a single degree. This is not roughly aligned, it is astronomically precise. To accomplish this, the builders needed more than a simple sundial. They required a sustained, sophisticated program of celestial observation, likely tracking the circular path of a specific star around the celestial pole, or using the bisection of the angle between the rising and setting points of a star on the horizon. This was a society that could translate the grand, slow turn of the night sky into a perfectly oriented square on the ground, a process requiring both profound astronomical knowledge and flawless surveying technique. Yet the mastery penetrates the stone itself. Look inside to the network of internal passageways. The descending passage, for instance, extends over 300 feet into the bedrock at a consistent, steep angle. Its straightness is remarkable, deviating from a perfect line by less than a quarter of an inch over its entire length. The same is true for the ascending passage and the grand gallery. Carving such straight, long, and accurately angled tunnels through solid limestone from both ends to meet in the middle is an engineering puzzle that still captivates architects. This level of accuracy at such a monumental scale is not the product of guesswork or trial and error. It screams of advanced planning. It implies the use of detailed architectural plans, a standardized, highly accurate unit of measurement repeated consistently by hundreds of workers, and a command of geometry so complete it could be executed perfectly in 3 dimensions. This points not to a society of brute force laborers, but to a highly organized, technically capable civilization with specialized knowledge passed down through a trained, likely literate, priestly or engineering class. The pyramid is not just a tomb, it is a permanent testament in stone to a forgotten science of measurement and alignment, a science so refined that its methods remain one of history's most compelling and debated mysteries. The pyramids of Egypt represent a civilization's obsession with celestial order, but in the dense jungles of Central America, a different culture pursued a more enigmatic form of perfection. Scattered across the Diquis Delta of Costa Rica, as if forgotten by giants, lie hundreds of massive stone spheres. These are not rough, natural boulders. They are deliberate creations carved from hard gabbro, limestone, and sandstone into shapes of breathtaking precision. Their sizes range from that of a simple fruit to colossal orbs over 2 meters, or 6.5 feet in diameter, weighing many tons. What stuns archaeologists is not their existence but their flawless geometry. Many of these spheres are near perfect, their sphericity and surface smoothness consistent to within millimeters. Achieving this without the aid of modern lathes, lasers, or even metal tools is a quiet marvel of patient engineering. The likely process reveals a profound, tactile understanding of material. Artisans probably began by selecting a suitable boulder, then using heat to create controlled fractures, breaking away large, unwanted portions. The real mastery began in the next phase, a testament to immense patience and skill. Using hammerstones of a harder material, they would have painstakingly pecked away at the surface, gradually reducing the form, turning it, and pecking again, over months or even years. Finally, the sphere would be ground and polished with sand and water, perhaps using leather or another flexible material, to to achieve that impossibly smooth, uniform finish. This was not a quick monument, it was a sustained, generational act of craftsmanship. The purpose of these spheres deepens the mystery. Some were found arranged in lines or geometric patterns, leading to theories they served as astronomical markers, aligning with celestial events. Others believe they denoted status, with the largest spheres marking the homes of powerful leaders or sacred spaces. They may have even served as territorial boundaries, silent sentinels defining the landscape. While their original meaning may be lost, their creation speaks a universal language of technical mastery. They signify a culture that had moved beyond purely functional stonework into a realm of abstract, mathematical idealism. To look at one of these spheres is to see a community that valued precision for its own sake, that possessed the collective will and specialized knowledge to transform a stubborn piece of the earth into a symbol of perfect harmony, a silent stone planet resting in the green heart of the jungle. That same Persian genius for mastering the elements did not stop at bringing water from beneath the ground. It reached upward into the very air, sculpting the wind itself into a tool for survival. Across the ancient cities of Persia, in what is now Iran, a unique and elegant silhouette rose above the flat rooftops, the Badgir or Windcatcher. In a landscape where summer temperatures could become unbearable, these structures were not mere decoration. They were the beating heart of a revolutionary, entirely passive form of air conditioning. A Badgir is essentially a tall, vertical tower, open at the top and divided internally into several vertical shafts. Its design is deceptively simple, yet its operation reveals a profound grasp of physics. The key lies in understanding that wind, even on a still day, is not uniform. There are almost always gentle breezes flowing high above the ground, breezes that a structure at street level would never feel. The Badgir acts as a giant scoop, capturing these cooler, faster-moving air currents at its pinnacle, but capturing the wind is only half the equation. The true innovation is in how the Badgir directs it. The captured breeze is funneled down one of the tower's internal shafts, which leads directly into the heart of the building below. As this cooler, denser air descends, it creates a natural pressure difference, effectively pushing the stale, warm air inside the structure out through another shaft or through open windows. This creates a continuous, gentle circulation, a natural breath for the building. The system could be refined to an art form. Often, the incoming air would be directed over a small indoor pool of water or through a moistened curtain. This introduced evaporation into the process, which absorbed heat energy from the air, cooling it even further before it flowed into the living spaces. The result was a dramatic and comfortable drop in temperature, all achieved without a single moving part, without any fuel, and in complete silence. The mastery here is bioclimatic, a perfect marriage of architecture and environment. Builders did not just construct a house, they designed an integrated system. They had to possess an intimate, localized knowledge of prevailing wind patterns, the sun's path, and even the thermal properties of their building materials like thick mud brick, which stored coolness at night and released it slowly during the day. Each Badgir was a custom solution, its orientation, height, and internal shaft design carefully calibrated to its specific location. This was not a one-size-fits-all technology. It was a responsive, intelligent adaptation. To stand in a room cooled by a centuries-old windcatcher is to experience a form of ancient wisdom that feels almost magical. It is a quiet, elegant reminder that technical mastery is not always about complexity or power consumption. Sometimes the most sophisticated solution is the one that listens to the natural world, understands its rhythms, and designs a graceful, enduring way to live in harmony with them. Above the cooling winds of Persia, a different kind of structural ambition was being carved from solid rock in the Bronze Age world. The entrance to the so-called treasury of Atreus in Mycenae is a statement of pure, intimidating power. This is not a doorway, it is a portal, a dark mouth leading into a hillside that whispers of kings and monumental effort. Its architectural genius is deceptively simple, yet it reveals a critical, experimental leap in how ancient builders thought about space and support. The innovation is the massive corbelled arch that frames the entrance. Unlike a true arch built with wedge-shaped stones locked by a central keystone, a corbelled arch is built through a patient, daring process of cantilevering. Imagine each horizontal course of stone blocks being laid, one on top of the other, but with each new layer set slightly inward, overhanging the one below. Layer by layer, the two sides of the doorway reach toward each other, until finally, at the apex, the gap is closed by a single capstone. This creates a triangular-shaped opening that is incredibly strong, distributing the immense weight of the earth and masonry above down through the angled sides. It was a brilliant solution for spanning a wide space without a single, impossibly long lintel stone. Yet the Mycenaean builders did not stop with the corbelled arch alone. They crowned it with a staggering display of logistical mastery. Directly above this ingenious arch, they placed a single, monolithic lintel block. This stone slab is estimated to weigh approximately 120 tons. To put that in perspective, it is heavier than many of the stones used in the Great Pyramid. Transporting this behemoth from a quarry and then lifting it precisely into place, over 20 feet above the ground, remains one of the great unsolved puzzles of Bronze Age engineering. The effort speaks of a society with extraordinary organizational control, capable of mobilizing and coordinating large workforces with a singular, precise goal. The entire structure, this combination of clever corbelling and brute force lifting, was a bold experiment in creating grandeur. It was a step toward mastering enclosed, domed spaces, leading eventually to the magnificent beehive-shaped interior of the tomb itself. This doorway, therefore, is more than an entrance to a resting place. It is a threshold in architectural history. It marks a moment when builders moved beyond stacking and began actively sculpting void from solid, using geometry and sheer will to defy gravity and create spaces that would awe the living and honor those who came before for millennia. Beneath the clear, blue waves off Japan's southernmost island lies a mystery that blurs the line between geology and human history. The Yonaguni Monument is a sprawling underwater formation, a series of immense, layered sandstone terraces that descend like a sunken stadium into the deep. What captures the imagination are its features: sharp 90-degree angles, perfectly straight edges, and flat platforms that appear meticulously leveled. There are structures that look like staircases climbing the submerged rock face, and isolated pillars standing apart from the main formation. To the untrained eye, it is an unmistakable cityscape, a silent Atlantis resting on the ocean floor. The scientific community, however, is deeply divided. Many geologists present a compelling natural explanation. The sandstone in this region is known to fracture along straight lines due to tectonic stresses, and the powerful currents of the area could erode the rock into these startlingly geometric shapes over millions of years. They argue that nature, through the patient tools of seismic activity and water, is a master architect in its own right. Yet other researchers counter with a series of troubling questions. Why are so many of these seemingly natural right angles and flat planes concentrated in one specific, complex formation? They point to what appear to be tool marks on certain surfaces and the presence of what looks like a carved human face, though heavily eroded. The monument's location adds another layer of intrigue. It sits directly on a major tectonic fault line, an area notorious for sudden, catastrophic subsidence. This opens a tantalizing possibility. Could an entire complex of structures built on this unstable coast thousands of years ago have been swallowed by the sea in a single dramatic event? If even a portion of the Yonaguni Monument is the work of human hands, the implications are profound. It would suggest a previously unknown seafaring culture with advanced stoneworking skills, thriving in the Pacific long before established historical timeline. This culture would have possessed not only the technical mastery to quarry and shape massive sandstone blocks, but also the nautical knowledge to navigate these treacherous waters and coordinate a large-scale building project on a coastline vulnerable to the very Earth's movements. The monument, therefore, is more than a geological curiosity. It is a profound riddle. It forces us to confront the limits of our historical maps and to wonder what other chapters of human innovation may lie submerged, not lost to time, but to the restless, rising sea. High in the Andes, a different kind of thread connected an empire. The vast Inca road system was a marvel of logistics, a stone ribbon stretching over 25,000 miles across some of the most extreme topography on Earth. But where these roads met the terrifying void of a mountain gorge, the Incas performed an act of engineering that seems to defy both physics and time itself. They built suspension bridges from woven grass. These were not crude rope ladders, but sophisticated, load-bearing structures that spanned distances of over 150 feet across dizzying drops. The most famous surviving example is the Sacsayhuamán Bridge, a living testament to this ancient innovation, still rebuilt by hand every single year in a continuous tradition. The entire process is a masterclass in applied physics using organic materials. It begins with the harvesting of a tough local grass called iku. Community members twist the grass into thin cords, then twist those cords together into larger ropes, and finally, braid those ropes into the massive main cables that will carry the entire bridge's weight. This technique, creating ever thicker and stronger cables from weaker individual fibers, is a direct application of tensile strength principles. The cables, each as thick as a human torso, are then carried to the canyon's edge. Here, the Inca's stoneworking skill came into play again, as the cables were anchored to massive stone abutments, ingeniously carved and fitted to handle immense pulling forces. Once the main cables were secured across the chasm, a delicate but strong deck of woven mats and additional ropes was suspended below them, with handrails added for stability. The finished bridge possessed a flexible strength perfectly suited to its environment. Unlike a rigid stone bridge, the woven grass could sway and absorb the energy of howling mountain winds and the dynamic, bouncing load of crossing travelers. It moved with the forces acting upon it rather than fighting them, a principle at the heart of modern seismic engineering. The annual rebuilding is not due to weakness, but to a profound understanding of sustainability and community. The organic materials would naturally degrade over time, but by making renewal a sacred, communal ritual, the Incas ensured the bridge's permanence through perpetual care. This cycle transforms the bridge from a mere tool into a living entity, its strength derived as much from shared knowledge and collective effort as from the grass itself. To cross the Sacsayhuamán today is to walk on a thread of history, feeling it breathe and shift underfoot. It is a powerful reminder that technical mastery does not always require steel and concrete. Sometimes the most resilient connection is woven from the very landscape it conquers, a testament to human ingenuity that bends but never breaks. Deep beneath the sunlit island of Malta, a different kind of mastery was being carved into the soft limestone. The Hypogeum of Sacsayhuamán is not a structure built upward, but one excavated downward, a labyrinth of chambers and passages spanning 3 levels, all painstakingly hollowed out from the living rock over centuries, beginning around 3,300 years before the Common Era. This underground sanctuary, a resting place and ceremonial site, holds a secret that only reveals itself in silence. In certain chambers, a low hum or a spoken word does not just echo, it transforms. The space itself seems to awaken, resonating at specific, powerful frequencies. One chamber in particular, known today as the Oracle Room, possesses an acoustic phenomenon that feels almost supernatural. A voice spoken at the correct pitch within this small, circular room can be heard with perfect clarity in every other part of the sprawling, multi-level complex. It is as if the entire subterranean world becomes an ear tuned to a single, sacred sound. This was almost certainly not an accident. The builders carved, shaped, and smoothed these underground halls with an intent that went beyond mere shape. They were sculpting sound itself, achieving such a precise acoustic effect in an excavated space where you cannot simply add or move a wall, represents a profound, intuitive grasp of physics. It suggests the artisans understood how sound waves travel, how they reflect off curved surfaces, and how certain spaces can amplify specific frequencies through resonance. They were not just architects, they were the earliest known audio engineers, turning architecture into a monumental instrument. This mastery of acoustics likely served a profound ritualistic purpose. In the flickering torchlight of the deepest chambers, a priest's chant or a ritual drumbeat would not merely be heard, it would be felt, vibrating through the stone and the very bodies of those gathered. This could induce altered states of consciousness, creating an immersive, overwhelming sensory experience that bridged the physical world and the spiritual one. The Hypogeum, therefore, stands as a testament to a forgotten science of the senses. Long before the Greeks theorized about harmonics, these Neolithic builders were practicing the principles, using the earth itself to compose a sacred symphony meant not for entertainment, but for transcendence, proving that technical mastery could be channeled to touch the human spirit as powerfully as it shaped stone. While ancient builders mastered acoustics and suspension bridges, another culture achieved a different kind of perfection, one measured not in sound or flexibility, but in defiance of time itself. In a quiet corner of Delhi, a simple iron pillar has stood undisturbed for over 1,600 years. It bears no intricate carvings, no grand architectural flourishes, yet its very existence is a quiet revolution in metallurgy. The pillar, over 23 feet tall, was forged from a single, massive piece of wrought iron, a feat of smelting and forging that would be impressive enough. But its true, unsettling genius lies in what has not happened to it. In a region with distinct wet and dry seasons, subjected to over a millennium of monsoons, humidity, and pollution, this iron pillar shows almost no signs of rust. It is not merely old, it is virtually immune to the relentless decay that claims nearly every other piece of exposed iron on the planet. This is not a result of some magical alloy unknown to modern science. Through careful analysis, researchers have uncovered the pillar's secret, a brilliant accident of ancient craftsmanship that reveals a profound, if perhaps intuitive, mastery of material science. The iron used to create the pillar possesses a very specific chemical signature, a high phosphorus content combined with a very low sulfur content. This unique composition is the key. During the forging process, the high phosphorus prevented large amounts of carbon from mixing in, which kept the iron relatively pure and less prone to certain types of corrosion. More importantly, over centuries of exposure, this particular blend of elements allowed a thin, protective film to form on the pillar's surface. This film, a stable compound called mesawite, acts as a perfect, self-renewing shield. It is a passive layer that prevents oxygen and moisture from reaching the raw iron beneath, effectively putting corrosion into a permanent state of arrest. The incredible part is that achieving this specific chemical balance was no simple task for ancient metalworkers. It required an extraordinary level of process control, from selecting the right iron ore to managing the temperature and airflow in the furnace, to the precise hammering and shaping of the final product. They had to consistently produce iron of a purity and composition that would not be reliably replicated in the West until the dawn of the industrial era, over 1,000 years later. This suggests these artisans were not just skilled laborers, they were empirical chemists. Through generations of trial, observation, and passed down knowledge, they perfected a recipe and a technique that yielded a material capable of a near-eternal vigil. The pillar, therefore, is a testament in the truest sense. It does not shout its secrets, it simply stands, a silent, unchanging witness to a level of technical mastery so advanced that it patiently waited for modern science to finally understand its quiet, rustless perfection. The silent defiance of the Delhi iron pillar stands in stark contrast to a different kind of monumental challenge, one that required moving giants rather than preserving metal. On the most remote inhabited island on Earth, a society in complete isolation performed a logistical miracle. Easter Island, or Rapa Nui, is dotted with nearly 900 massive stone figures called moai. These are not small carvings. The largest completed moai, named Paro, stands over 30 feet tall and is estimated to weigh a staggering 82 tons, the weight of a fully loaded commercial jetliner. They were meticulously carved from compressed volcanic ash at a single quarry in the heart of the island. But their journey had only just begun. From the quarry slopes, these multi-ton giants then had to travel up to 11 miles across rugged, hilly terrain to reach their permanent ceremonial platforms called ahu along the coast. For centuries, the method of their transportation was one of archaeology's greatest riddles. How could a society with no wheels, no large animals, and no metal tools possibly orchestrate such a feat? The answer, emerging from both modern experiments and revived oral traditions, is as ingenious as it is daring. The statues may have literally walked. Researchers, collaborating with local communities, tested a method described in ancestral stories. By carefully attaching ropes to the top and base of a concrete replica moai, teams could rock the statue from side to side, using its own rounded base as a pivot. With each coordinated pull, the giant would tilt forward, landing just a few inches ahead of its previous position. It was a slow, rhythmic, and profoundly skillful process, a form of upright, controlled waddling. This walking theory hinges on a deep, intuitive understanding of physics. The teams manipulating the ropes had to work in perfect unison, applying force at precisely the right moment to maintain the statue's balance. They were essentially managing the moai's center of gravity in motion, preventing a catastrophic fall that would shape the valuable work of years. It was a dance with mass and momentum, where a single misstep could mean disaster. This was not brute force dragging, it was dynamic, coordinated engineering. The implications of this method reveal the true mastery of the Rapa Nui people. Transporting even a single moai in this way would have required the synchronized labor of dozens, if not hundreds, of individuals. It demanded not just muscle, but communication, leadership, and a shared, unwavering commitment to a communal vision. In a landscape with limited resources, where every calorie of food and every strand of rope was precious, this represents an astonishing investment of social capital. The moai were more than statues, they were the physical manifestation of a society's unity, its ancestral reverence, and its ability to solve seemingly impossible problems through collective intelligence and innovation. Their silent march across the island stands as a powerful testament to what human communities can achieve in even the most isolated and challenging circumstances, not by conquering nature with overwhelming technology, but by understanding its laws and working together in rhythm with them. While the moai walked across their remote island, a different kind of descent was being carved into the earth on the Indian subcontinent. Here, necessity gave birth to an architecture of profound beauty and ingenious design, the stepwell. Far more than a simple well, these were inverted palaces, multi-storied structures that descended deep into the ground to meet the retreating water table during the long, dry seasons. One of the most breathtaking examples is Chand Baori in Rajasthan, a colossal geometric chasm that seems to defy the very logic of construction. Its form is staggering, a precise square that plunges over 100 feet down, with 3 of its sides lined by a symmetrical maze of staircases. 13 stories of steps over 3,500 individual stones create a hypnotic, repeating pattern that draws the eye into the cool, dark depths where a reservoir of green water waits. This was not an accidental beauty. It was a masterpiece of intentional design serving multiple, vital functions. The sheer number of steps provided access to the water at every possible level, ensuring that as the water receded in the heat, the community could always reach it. But the stepwell's genius was also social and environmental. Its deep, shaded interior created a natural refuge from the blistering sun above, a cool, subterranean oasis where travelers could rest and communities could gather. The architecture itself became a climate control system, with the water at the bottom acting as a natural coolant, pulling warmer air down and allowing cooler air to circulate through the stepped galleries. The engineering challenge was immense. Building such a vast, open structure underground meant carefully managing the immense lateral pressure of the surrounding earth. The builders solved this through their precise, repetitive geometry. The step design, with its numerous terraces and reinforced walls, distributed the soil's pressure evenly, acting like a series of retaining walls that braced against each other. This required an advanced understanding of statics and soil mechanics, all calculated without modern engineering software. Every stone was precisely carved and placed not just for stability, but to create that mesmerizing visual rhythm, blending absolute utility with breathtaking artistry. Chand Bayori and stepwells like it were the beating heart of their communities, centers for water, for social life, and for spiritual reflection. They stand as a powerful testament to a philosophy where solving a fundamental human need did not mean sacrificing beauty, but rather that the most elegant solution was often the most beautiful one, a functional wonder carved directly into the body of the earth. From the cool, subterranean depths of the stepwells, we emerge onto one of the most stark and puzzling canvases on Earth. The Nazca Desert of southern Peru is a vast, silent plateau, a landscape of reddish-brown pebbles under a relentless sun. Yet from this barren ground, an ancient culture pulled forth immense, elegant shapes that can only be truly seen from the sky. These are the Nazca Lines, a gallery of geoglyphs so large they redefine our understanding of ancient planning and precision. Etched not by adding material, but by subtraction, the creators meticulously removed the dark, oxidized surface stones to expose the lighter, creamy soil beneath. This simple act of contrast created lines that have endured for over 2,000 years. The figures themselves are breathtaking in their variety and scale. A hummingbird with wings outstretched, a spider with perfectly proportioned legs, a monkey with a spiraling tail, and a condor with a wingspan that stretches the length of multiple football fields. Some of these drawings are over 1,200 feet long, their outlines clean and continuous as if drawn by a single, steady hand on a colossal sketchpad. The true mark of technical mastery here is not in the complexity of the tools, which were likely simple stakes and ropes, but in the flawless execution of such enormous designs across miles of uneven, rocky terrain. Imagine trying to draw a perfect 1,000-foot circle on a hillside without ever being able to step back and see your work. The Nazca people solved this puzzle through brilliant scaling and coordination. Researchers believe artists first created small-scale models of their designs. These models could then be translated to the desert floor using a basic but effective surveying technique. By establishing a central axis line and using a network of guideposts placed at key points, workers could systematically replicate the design, section by section, maintaining its perfect proportions as it ballooned to a monumental size. This required not just artistic vision, but a commander's grasp of geometry and trigonometry. Every curve, every angle, every intersection had to be calculated and communicated to teams of workers who would then clear the stones along the prescribed path, ensuring the lines remained crisp and unbroken. This was a feat of large-scale project management, a communal artwork that demanded the synchronized effort of a coordinated workforce, all working toward a single, invisible image that none of them could ever see in its entirety. This leads us to the enduring enigma, the why. For whom or what were these magnificent lines intended if the people who made them could never behold their own handiwork? The most supported theories look not to the horizon but to the heavens. Many of the lines align with celestial events like the solstice sun or the rising points of important stars. Others may have served as sacred pathways for ritual processions, their forms representing mythological beings or spiritual symbols. The very act of creating them, of walking these immense patterns into the earth, may have been a form of devotion or a way to communicate with the gods above. The lines transform the desert from a wasteland into a ritual landscape, a permanent prayer etched into the skin of the planet. Their purpose may be lost to us, but their legacy is one of stunning clarity. They stand as a powerful testament to a culture that could hold a complex geometric idea in its collective mind and then imprint it upon the world with unwavering precision. A reminder that human ambition can sometimes find its purest expression not in towering monuments, but in vast, elegant drawings meant for an audience of gods, spirits, and the endless sky. While the Nazca Lines transformed a desert into a celestial map, another civilization was mastering the art of moving something far more essential, not across land but above it. The Pont du Gard in southern France is more than a bridge. It is a river of stone built to carry a river of water. This colossal three-tiered Roman aqueduct strides across the Garden River Valley with an air of serene, unshakable confidence. Its genius lies in a perfect marriage of brute strength and delicate calculation, all achieved without a single drop of mortar binding its golden limestone blocks. Each stone was cut with such precision that it fits against its neighbor by gravity and friction alone, locked in place with iron clamps to resist the lateral forces of wind and water. This dry stone construction reveals a breathtaking level of craftsmanship where the margin for error was virtually zero. But the true measure of Roman mastery is not in the bridge itself, but in the invisible line it served. The Pont du Gard was just one critical link in an aqueduct system that stretched over 30 miles from a spring to the bustling city of Nemesis, modern-day Nimes. To maintain a steady, gentle flow across that entire distance, Roman surveyors faced an engineering puzzle of the highest order. The water channel needed a constant, shallow downhill slope. The gradient they achieved is almost incomprehensible in its accuracy, a drop of only 1 foot for every 3,000 feet of length. This means over its entire 30-mile journey, the aqueduct descended only about 55 feet. Achieving this required surveying the rugged French countryside with a level of precision that rivals modern projects. Using simple tools like the Corbelled, a long water level, teams of surveyors had to map a path that would maintain this imperceptible slope across hills, through tunnels, and over valleys. A miscalculation of even a few inches could mean the water would flow too slowly and stagnate, or too quickly and burst its channel. The Pont du Gard itself is the spectacular solution to one of the route's greatest obstacles. Its 3 tiers of arches are a textbook example of efficient force distribution. The largest 6 arches form the bottom tier, supporting the immense weight of the structure and the water channel above. The middle tier of 11 arches and the top tier of 35 each bear a progressively lighter load, creating a structure that is both monumentally strong and visually graceful, growing lighter as it reaches for the sky. This was engineering as public art, a statement of civic power and technological triumph meant to inspire awe in every citizen who saw it. For centuries, it delivered life-giving water to a distant city, a silent, enduring symbol of an empire's ability to bend geography to its will. The Pont du Gard stands not as a ruin, but as a testament. It embodies the Roman ideal where the most formidable functionality was inseparable from aesthetic grandeur. proving that the highest technical mastery seeks not just to solve a problem, but to elevate the solution into something timeless. The silent symphony of the Hypogeum was carved beneath the earth, but on the sun-baked surface of Malta, a different kind of architectural ambition was reaching for the sky. Scattered across these Mediterranean islands are structures so ancient they predate Stonehenge and the Great Pyramids by over 1,000 years. The megalithic temples like Hypogeum are not just old, they are pioneers. They represent humanity's first daring experiments in creating monumental, roofed architecture entirely from stone. Their builders looked at the rugged local limestone and saw not just building blocks, but the potential for sacred space. The challenge was immense: how to create a chamber wide enough for communal ritual without the roof collapsing under its own weight. Their ingenious solution was a technique we've seen before, but here applied on a staggering scale: corbelling. They would lay enormous stone slabs as walls, then carefully set the next layer of slabs slightly inward, overhanging the first. Layer by patient layer, they would narrow the gap, creating a soaring, beehive-shaped ceiling that distributed the crushing weight down through the walls. But the true show of force came with the roof spans themselves. At the climax of this corbelled vault, the builders would cap the chamber with truly monstrous limestone slabs, some weighing over 20 tons. These were not merely placed, they were precisely engineered keystones, the final, locking piece that made the entire vault stable. Think of the coordination this required. First, quarrying these multi-ton blocks from the bedrock using only stone and wooden tools, then transporting them across miles of rough terrain, likely on rollers made from tree trunks, to the sacred site. Finally, the most perilous phase, lifting them into position, perhaps using earthen ramps and a system of ropes and levers to settle them perfectly atop the waiting walls. One slip, one misaligned stone, and the entire chamber could be compromised. This was not the work of a scattered, simple society. It speaks of a stable, organized culture with a deep pool of specialized knowledge. There must have been master architects who could visualize these complex spaces in 3 dimensions, planners who could manage the logistics of multi-year projects, and skilled laborers who passed down precise stoneworking techniques through generations. The temples were more than buildings, they were a collective act of faith and engineering, creating permanent homes for ritual in a world of impermanent materials. To stand inside Hypogeum today is to stand in one of humanity's very first attempts to enclose grandeur, to sculpt not just form, but atmosphere and awe from solid rock, a testament to a forgotten society that looked at a slab of limestone and saw the dawn of architecture itself. The ambition to build monuments that touch the heavens is matched only by the need to understand the unpredictable forces that shake the earth from below. In the year 132, during China's Han Dynasty, a brilliant polymath named Zhang Heng presented the emperor with a device that seemed to belong to a far future. He called it the Hufeng Didongyi, an instrument for measuring the seasonal winds and the movements of the earth. To the court, it appeared as a magnificent bronze urn about 6 feet in diameter, adorned with artistic splendor. But this vessel was no mere ornament, it was the world's first known seismoscope, a machine designed to detect the invisible tremors of distant earthquakes. Its operation was a spectacle of mechanical poetry. Encircling the urn's upper section were 8 sculpted dragons, each facing one of the primary cardinal and intercardinal directions: north, south, east, west, and the points between. Crouched directly below each dragon was a corresponding bronze toad, its mouth open in anticipation. Inside the sealed vessel, Zhang Heng had engineered a hidden mechanism, the true heart of his invention. Historians believe it centered on a delicately balanced inverted pendulum, suspended to swing freely. When seismic waves, traveling hundreds of miles from an epicenter, finally reached the capital, they would cause the ground to tremble ever so slightly. This subtle motion would set the internal pendulum swinging. Its movement would trigger a clever series of levers and linkages, which would in turn activate only one of the 8 dragons. That single dragon would tilt its head and release a bronze ball held in its jaws. The ball would drop with a resonant clang directly into the waiting mouth of the toad below, providing both an audible and visual signal. The direction the dragon faced told court officials the compass bearing from which the earthquake waves had originated. The genius of Zhang Heng's device lies in its elegant simplicity and its profound scientific insight. It demonstrated an understanding that seismic energy propagates in waves with a specific directionality, and that this directional information could be captured and displayed mechanically long before the shaking was felt locally. It transformed an invisible, mysterious, and often frightening natural phenomenon into something quantifiable and measurable. The device was reportedly successful on multiple occasions, once even detecting a quake so distant that no one in the capital had felt a tremor, a report that was met with skepticism until messengers days later arrived from the affected region hundreds of miles away, confirming the event. This achievement reveals a mindset far ahead of its time. Zhang Heng was not merely an inventor, he was an early seismologist. His seismoscope embodied a desire to move beyond superstition and myth in explaining natural disasters, to replace fear with data. It married the artistic sensibility of the era with a razor-sharp mechanical logic, proving that the quest to understand our planet's restless nature is a timeless human pursuit. In that single, beautiful bronze vessel, we see the dawn of instrumental geophysics, a quiet ball dropping into a toad's mouth signaling not just a direction, but the very moment humanity began building machines to listen to the secret vibrations of the world itself. Zhang Heng's seismoscope listened to the Earth's deep tremors, but Roman engineers sought to tame a more immediate elemental force for daily life, the bitter cold of winter. Their solution was an invisible luxury, a whisper of warmth rising from the very floor itself. In the grand bath complexes and luxurious villas of the empire, they perfected a system of central heating so effective it would not be matched in Europe for over a millennium, the Hypogeum. This was not a simple fireplace in the corner, it was a fully integrated climate control system, a hidden circulatory network for hot air built directly into the architecture. The process began in a dedicated furnace room, the Persian, often manned by a slave who maintained a constant fire, but the genius lay in what happened next. The floor of the room to be heated was not laid directly on the ground. Instead, it was raised on a grid of short, sturdy brick pillars called pilae. These pillars created a hollow space, a plenum, beneath the entire floor. Meanwhile, the walls were often constructed as double shells, with rectangular box tiles creating vertical channels inside them. The hot air and smoke from the furnace were channeled directly into this subfloor cavity. From there, the heat would rise naturally, spreading evenly across the entire space, warming the thick tile or stone floor above before being drawn upward through the wall ducts. Finally, the spent gases would escape through carefully placed terracotta flues in the roof, creating a constant, gentle draft that pulled fresh hot air through the system. The result was a radiant, enveloping warmth that heated the room from the ground up without any smoky, drafty discomfort. This was engineering in service of comfort and public health on a grand scale. In the vast public baths or thermae, the Hypogeum was essential. It allowed for a progression of heated rooms from the warm tepidarium to the intensely hot coldarium, each with its own carefully regulated temperature, facilitating the Roman bathing ritual, which was as much about socializing and hygiene as it was about relaxation. But to make this possible required a deep, applied understanding of several principles. Builders had to master airflow dynamics, ensuring the channels were clear and sized correctly to promote circulation without allowing dangerous backdrafts or smoke leakage. They needed a grasp of basic thermodynamics, understanding how heat rises and how to distribute it through a network. And crucially, they had to select and use fireproof materials, terracotta tiles, and a special, slow-setting concrete that could withstand constant exposure to high temperatures without cracking. The entire system was a testament to meticulous planning, embedded into the very blueprint of a building. It could not be added as an afterthought. The Hypocaust represents a societal choice, a significant investment of resources and labor not for defense or ostentation, but for the quality of daily life. It speaks of a civilization that had moved beyond mere survival to actively engineer comfort, to create spaces of warmth and community even in the depths of winter. To walk on a floor warmed by a silent, ancient fire below is to connect with a very human aspiration, the desire to shape our environment, not just endure it, using ingenuity to turn the raw elements into a gentle, sustaining breath of heat. A mandala is a sacred diagram, a cosmic map meant to guide meditation. In the 9th century, on a lush Indonesian plain, a civilization of architects and artisans did something astonishing. They built one in stone at a scale meant to be walked through. The Borobudur temple is not merely a building you visit, it is a spiritual landscape you ascend. Its form is a perfect architectural allegory, a massive step pyramid consisting of 6 meticulously carved square terraces, crowned by 3 serene circular platforms. This is not random geometry, it is a direct, 3-dimensional representation of the Buddhist cosmos. The entire structure is a single, unified teaching, a physical path from the world of earthly desires at the base, up toward the realm of formlessness and enlightenment at the summit. The journey begins in the Kamadhatu, the sphere of desires, depicted in hidden reliefs at the temple's foot that illustrate the consequences of worldly attachment. As pilgrims climb clockwise along the narrow corridors of the first 4 square galleries, they are surrounded by a staggering tapestry of stone. Over 2,600 intricately carved relief panels unfold like a sacred comic strip along nearly 3 miles of wall space. These are not decorations, they are scripture in stone depicting the life of the Buddha, tales of his past lives, and scenes of daily life in ancient Java, all serving as visual lessons on karma, morality, and compassion. The artistry here is breathtaking, each panel a masterclass in narrative carving, designed to be read and reflected upon step by step. After navigating these galleries of form and story, the pilgrim's path undergoes a profound shift. The climb transitions from the square, ordered terraces to the open, circular platforms above. Here, the narrative reliefs vanish. Instead, 72 latticed stupas, each housing a serene stone Buddha statue, sit in silent, concentric circles. The final, central stupa at the very peak is empty, or perhaps full of the unspeakable, symbolizing ultimate enlightenment, nirvana itself. This architectural progression from the complex to the simple, from the narrative to the abstract, from the square to the circle, is the core of the temple's genius. It physically enacts the spiritual journey from the illusion of a separate self through moral and intellectual understanding, finally arriving at a state of pure, undifferentiated awareness. The technical mastery required to execute this vision is humbling. The entire monument is constructed from over 2 million blocks of andesite stone, fitted together without any mortar, relying solely on precise interlocking joints. Its builders had to maintain perfect geometric symmetry across its vast dimensions, while simultaneously orchestrating the work of countless sculptors to ensure narrative continuity across those thousands of panels. This was a project that demanded not just artistic skill and brute labor, but a deep, shared philosophical understanding among the entire community, from the master architects down to the stone carvers. Every chisel stroke, every placed block, was an act of devotion and a precise contribution to a grand cosmological diagram. Borobudur is perhaps the ultimate fusion of engineering and spirituality. It is architecture as a verb, a structure designed not just to be seen, but to be experienced with the body and the mind, guiding the faithful along a predetermined path of awakening. It stands as a monumental reminder that the greatest technical achievements are often those that serve a purpose beyond the physical, giving permanent, tangible form to humanity's most profound questions about the nature of existence itself. High on a lonely sandstone butte in Choco Canyon, a secret was carved into the rock that only the sun could tell. Atop Fajada Butte, 3 massive stone slabs lean against the cliff face. Behind them, a spiral petroglyph is etched into the stone. For most of the year, this carving sits in shadow, a silent, unremarkable design. But on specific, crucial days, a transformation occurs. As the sun climbs to its zenith, a sliver of light slices between 2 of the giant slabs. This sharp, brilliant dagger of sunlight pierces the center of the spiral, bisecting it with perfect geometric clarity. Then, as the sun moves, the light dagger travels, tracing a path across the carved symbol before vanishing. This is not a random play of light and shadow. It is a meticulously engineered celestial clock, known today as the sun dagger. The phenomenon marks the summer solstice with a vertical beam that cuts directly through the spiral's heart. At the winter solstice, 2 daggers of light perfectly bracket the spiral on either side, and during the equinoxes, a smaller, distinct dagger of light appears, touching a different part of the carving. This was a solar calendar of astonishing precision, built not from moving parts, but from the immovable marriage of geology and astronomy. The genius of the ancestral Puebloan builders lies in their patient, profound observation. They did not construct this calendar, they discovered it within the landscape and then enhanced it. They positioned the 3 multi-ton slabs with deliberate, careful intent. The exact angle and spacing of these stones were everything, acting as a natural aperture, a cosmic lens that filtered the sun's rays to create the specific light patterns they needed to see. This required a deep, generational understanding of the sun's changing path across the sky throughout the year. They had to know precisely where the sun would rise and set on the horizon at the solstices and equinoxes, and then calculate how its midday light would interact with this specific rock face at this specific latitude. This was astronomy made permanent, a way to pin the abstract, cyclical motion of the heavens to a fixed point on Earth. The purpose of such a precise calendar was deeply practical, yet spiritually profound. In the arid, challenging environment of the Southwest, timing was everything. Knowing the exact date of the solstices and equinoxes allowed the community to anticipate the changing seasons with certainty. It told them when to plant crops, when to harvest, and when to prepare for the coming cold or heat. This knowledge was the foundation of survival, allowing a sophisticated society to flourish in a land of scarcity. But the sun dagger's location, high on a remote butte, suggests its role extended beyond simple agriculture. The climb to reach it was likely a ceremonial act reserved for spiritual leaders or specific times of the year. The dramatic, fleeting appearance of the light dagger, illuminating a sacred spiral, would have been a powerful, awe-inspiring event. It connected the cycles of their daily lives directly to the grand, reliable order of the cosmos, reinforcing a worldview where human activity was in harmony with celestial law. The sun dagger stands as a quiet masterpiece of archaeoastronomy. It requires no maintenance, no interpretation, no priestly class to read its meaning. It simply is, waiting each year for the sun to return and speak its silent, luminous truth. In this simple alignment of rock and light, we see a technical mastery that is not about moving mountains, but about understanding the light that falls upon them, turning a cliff face into a timeless, self-operating clock that has kept perfect time for 1,000 years. The sun dagger marked time on a solitary butte, but across the vast, featureless expanse of the North Atlantic, another culture faced a far more fluid and dangerous kind of navigation. For the Vikings, the open sea was not a barrier but a highway, and their legendary voyages to Iceland, Greenland, and even North America required a way to navigate when the sky itself betrayed them. Their most ingenious tool was not a map or a compass but a small, unassuming crystal. Norse sagas speak of a mysterious sunstone, a magical object that could reveal the hidden sun. Modern research suggests this was not magic, but a brilliant application of a natural optical phenomenon, likely using a transparent crystal of Iceland spar, a form of calcite. This crystal possesses a unique property called birefringence, meaning it splits a beam of light into two separate rays. On a completely overcast day, or during the twilight hours when the sun is just below the horizon, the light filtering through the clouds is polarized, meaning its waves vibrate in a specific orientation. To the naked human eye, this polarization is invisible, but to a navigator holding a piece of Iceland spar, it became a key. By rotating the crystal and looking through it toward a patch of clear sky, the navigator would observe the two split beams of light appearing with different brightnesses. The point where the two beams appeared equally bright would indicate the direction of the hidden sun, as the crystal's alignment directly correlated with the polarization pattern in the sky. This was celestial navigation stripped to its most essential physical form. It did not rely on seeing the sun itself, but on reading the subtle signature it left upon the very fabric of daylight. This practical use of optical mineralogy reveals a Viking mastery that was deeply empirical and sophisticated. It demonstrates a profound observation of the natural world, an understanding that even when the primary celestial marker was gone, its influence could still be detected and measured through the right natural instrument. This knowledge allowed Viking captains to maintain a course across hundreds of miles of open ocean with remarkable confidence, even in the notoriously gloomy weather of the northern seas. The sunstone represents a different kind of structural innovation, one of guidance rather than construction. It was a portable, personal technology that extended human perception, turning a simple crystal into a window to an invisible order. Its existence suggests a tradition of seafaring science, a body of practical knowledge passed down among navigators that enabled one of history's great ages of exploration, all guided by the hidden light held in the palm of a sailor's hand. The hidden light of the sunstone guided ships across a trackless sea, but the greatest test of architectural wisdom is not navigation, it is permanence. In the high desert of New Mexico, against a backdrop of sagebrush and piercing blue sky, a cluster of multi-storied buildings rises from the earth as if it grew there. This is Taos Pueblo, a community that has been continuously inhabited for over 1,000 years. Its structures are not monuments to a vanished past, they are living homes built from the very land they stand upon. The material is adobe, a humble mixture of earth, water, and straw hand-formed into bricks and dried by the sun. This simplicity, however, is the source of its profound genius. The thick adobe walls, often several feet deep, act as a massive thermal battery. They possess what engineers call high thermal mass. During the scorching summer days, the dense walls slowly absorb heat from the air, keeping the interior spaces remarkably cool and shaded. Then, as the desert temperature plummets at night, the stored warmth within the walls radiates gently back into the rooms, providing a natural, steady heat. This passive climate control creates a stable, comfortable environment year-round, without any need for mechanical systems or external fuel. The design extends this harmony. Buildings are oriented to maximize winter sun exposure while minimizing the harsh summer rays, and the use of small, recessed windows further helps regulate light and temperature. But the true mastery of Taos Pueblo is not just in the physics of its walls, it is in the sociology of its construction and the philosophy it represents. This is architecture as a continuous communal practice. The buildings are maintained and renewed through a collective effort, with new layers of adobe plaster applied regularly, a ritual that literally reconnects the community to its home and to each other. The very substance of the walls requires this ongoing care, creating a sustainable cycle where the structure is never finished, but is perpetually preserved through shared labor and knowledge passed from one generation to the next. The layout itself, with shared walls and common plazas, fosters a deep sense of interconnectedness. This is not a collection of private fortresses, but an organic, integrated village designed for mutual support. In a world now urgently seeking sustainable solutions, Tao's Pueblo stands as a quiet, powerful teacher. It demonstrates that the most advanced technical mastery can be found not in complexity or imported materials, but in a deep, intuitive dialogue with a specific place. It shows that resilience is built not through conquering an environment, but through understanding its rhythms and crafting a way of life that moves with them, a testament to the enduring power of building with, not against, the earth. The enduring wisdom of adobe teaches us to build in harmony with the land, but the ancient Greeks sought harmony of a different kind, a perfect marriage between human voice and open air. In the tranquil hills of Epidaurus, a stone bowl carved into the slope holds a secret that has captivated visitors for over 2,000 years. An actor standing on the circular stage, the orchestra, can speak in a normal, conversational tone, and a person sitting in the very last row, over 50 meters away and nearly 23 meters above, will hear every syllable with crystal clarity. This is not a legend, it is a repeatable physical fact, a testament to an acoustic design so flawless it feels like magic. The achievement of the Greek theater was not an accident of architecture, but a deliberate, empirical science of sound. Every element was calculated. The steep, fan-shaped seating arrangement, the cavea, acts as a natural sound reflector. The rows of limestone seats are not just benches, they function like a vast, textured filter. Their porous surface and precise, stepped angles naturally scatter and absorb the muddy, low-frequency rumble of wind and crowd noise, while allowing the higher frequencies of the human voice to carry cleanly upward. Even the placement of the stage itself was strategic, often backed by a building called the Skene, which helped project sound forward into the audience. This was an environment engineered for connection. In a society where theater was a vital part of civic and religious life, and where public oratory could shape the fate of a city-state, ensuring that every citizen could participate in the experience was a profound democratic act. It meant that the emotional weight of a tragic monologue, the precise argument of a political speech, or the witty punchline of a comedy could reach every single member of an audience of thousands, binding them together in a shared moment of art or ideas. The mastery here is one of elegant physics and deep social intention. The builders of Epidaurus understood how sound waves travel, reflect, and interact with materials on a grand scale. They transformed a hillside into a colossal, natural amplifier, creating a space where the human voice, in its most natural state, could achieve monumental reach. To sit in those sun-warmed stones today and listen to a whisper travel from the stage is to witness a dialogue with physics that has never ceased. It is a reminder that some of the greatest innovations are those we cannot see, but can only hear, feeling the invisible architecture of sound that still carries the echoes of an ancient, listening world. The human voice carries in a stone theater, but the idea that supports its very roof came from a much older, quieter revolution. Long before the grand arches of Rome, the concept was born from the most humble of materials, sun-dried mud. In the fertile plains between the Tigris and Euphrates rivers, the ancient Mesopotamians faced a constant architectural enemy, the scarcity of wood and stone. Their primary building block was the mud brick, a sturdy but limited material when used in the traditional post and lintel method, where a horizontal beam rests on two vertical posts. This method creates a fundamental weakness. the entire weight of the wall above bears down on the relatively small area where the lintel meets the posts, and the lintel itself is under constant tension, prone to sagging or snapping under heavy loads. The Mesopotamian solution was a stroke of geometric genius. They invented the arch by arranging specially shaped bricks in a curved, semicircular form. They transformed the physics of the structure. In an arch, each brick, called a voussoir, is cut like a wedge. When set in place and locked by a central keystone at the apex, a remarkable thing happens. The weight from above is no longer a downward force on a single point. Instead, it is converted into lateral, outward thrust, channeled along the curve of the arch and down through the supporting pillars or walls on either side. Every brick in the arch is now in a state of compression, being squeezed by its neighbors, a force that mud brick handles exceptionally well. This single innovation changed everything. It allowed for stronger, wider openings, like the imposing gateways of city walls that could withstand greater loads and the passage of time. But they did not stop there. By placing a series of arches side by side, they created the barrel vault, essentially a continuous arched roof. This was the breakthrough that enabled larger, more complex interior spaces. Suddenly, rooms did not have to be limited by the length of a single timber beam. A long, tunnel-like hall could be roofed entirely in brick, creating sturdy storage magazines, covered passageways, and more impressive ceremonial spaces. This was a fundamental leap in architectural thinking, moving from the simple logic of stacking to the sophisticated understanding of redirecting force through elegant geometry. It represents a moment when builders stopped seeing materials as limitations and started seeing shapes as solutions. The Mesopotamian arch and vault, born from earth and water, laid the invisible groundwork for the Pantheon's dome, the soaring naves of Gothic cathedrals, and the bridges that would one day span continents. It is a profound reminder that some of the most enduring ideas in human history are not made of stone or steel, but of insight, a simple curve in a brick that taught the world how to build stronger, wider, and reach further into the sky. These 25 silent testimonies are more than a collection of curiosities. They form a pattern, a shared language of human ingenuity spoken across continents and millennia. When we step back and view them together, certain profound themes begin to resonate. The first is a universal dialogue with the natural world. From the sun dagger's celestial alignment to the windcatchers' harnessing of invisible breezes, these innovations did not seek to dominate nature, but to listen to it. They represent a deep, sustained observation, a patient study of the sun's path, the wind's behavior, the properties of stone and soil and water. This was science in its purest, most applied form, knowledge gained not in isolated laboratories but through generations of living intimately within a landscape. A second powerful thread is the transformative use of local materials. True mastery often meant working with what was at hand, not importing solutions. The Incas wove bridges from mountain grass. The builders of Tao's pueblos shaped homes from the very earth beneath their feet. The Romans perfected a concrete born from their local volcanoes. This speaks to a principle of elegant adaptation, where the environment was not a limitation to be overcome with foreign technology, but a partner offering its own unique solutions. The genius lay in understanding the hidden potential within a block of limestone, a strand of fiber, or a pile of volcanic ash. Perhaps most importantly, these structures reveal a seamless integration of purpose. They were rarely built for a single, practical reason alone. The hypo-cost heated homes, but it also fostered community in public baths. Borobudur was a spiritual ascent carved in stone, yet its construction was a monumental feat of engineering and social organization. The Great Pyramid's precision served astronomical, religious, and political aims simultaneously. This unity of function, science, and belief suggests that for these cultures, the world was not divided into separate categories of the sacred and the practical. Technical mastery was a way to express cosmological understanding, to enact social order, and to solve physical challenges, all within a single, coherent act of creation. This collective view challenges a comforting story we often tell ourselves, the linear narrative of technological progress. We imagine a steady, upward climb from simple tools to complex machines. But history, as written in these stones and mechanisms, tells a different, more humbling tale. It reveals that peaks of profound mastery can arise, shine brilliantly for a time, and then fade from common knowledge, sometimes for centuries. The precision of the Antikythera mechanism was lost. The recipe for Roman concrete was forgotten. The method for moving the Moai fell out of practice. This is not a story of constant advancement, but one of brilliant, localized flowering of knowledge gained, held, and sometimes tragically let go. Therefore, these 25 innovations invite a fundamental shift in perspective. They ask us to stop viewing ancient achievements primarily as puzzles to be solved, or as anomalies that defy explanation. Instead, we can see them for what they are, clear evidence of the diverse and profound ways human societies have solved complex problems. They remind us that intelligence and creativity are not modern inventions, but timeless human traits. Each structure, from the humblest Qanat to the grandest pyramid, is a message in a bottle from a past civilization, saying simply, "We were here, we observed our world, and we found a way to build something meaningful within it." Their legacy is not a mystery, but an invitation to look at our own world with the same depth of observation, the same respect for materials, and the same unity of purpose that once raised these wonders from the dust. The interlocking stones of the Andes and the geared cosmos of the Antikythera mechanism are not isolated wonders. Together, they form a constellation of genius scattered across time and terrain, a powerful testament to a past far more technologically nuanced than our textbooks often convey. These 25 innovations dismantle a persistent myth, the idea that ancient societies were merely primitive precursors to our modern world. They reveal instead a vibrant, continuous thread of human ingenuity, a force as constant and defining as our own breath. This ingenuity was not about possessing advanced technology as we know it, but about possessing an advanced understanding. It was the profound ability to observe the world with relentless curiosity, to listen to the whispers of physics in wind and stone, and to craft elegant, enduring solutions from the materials at hand. Our ancestors were not waiting for a future of innovation. They were living it in their own sophisticated language of geometry, astronomy, and material science. As we face our own monumental challenges today, from designing sustainable cities to building resilient infrastructure for a changing climate, we might find our most valuable blueprints are not in the newest software, but in the oldest stones. The passive cooling of a windcatcher, the seismic flexibility of polygonal masonry, the self-healing chemistry of Roman concrete, these are not historical footnotes. They are masterclasses in working with nature rather than against it, in creating systems that endure because they are in harmony with fundamental, timeless laws. The future of innovation may very well depend on our willingness to look back, to see these ancient builders not as mysterious outliers, but as respected mentors. Their legacy asks us a final, compelling question. If so much profound knowledge was achieved, preserved in these silent structures, and yet still so much was lost to the tides of time, what other secrets remain buried? What chapters of our shared human story are still waiting, hidden in plain sight or deep beneath the earth and sea, ready to be rediscovered and reshape our understanding once more? We would love to hear which of these 25 innovations amazed you the most. Share your thoughts in the comments below, and if you are eager to join us as we continue uncovering the hidden chapters of our past, be sure to subscribe.